video, I went through simple machines and the classification of materials. To quickly recap on this classification of materials, we also learnt about elements, solutions, compounds, and mixtures. We'll go into some more detail on those now. We talked about metals, typically shiny. They are typically good conductors of electricity and heat. They are typically malleable and ductile. They're usually pretty strong. Ceramics can be strong. They're usually brittle. They usually don't conduct electricity or heat, and they're usually pretty hard, which we'll talk about what that term means in a second. Different to strength. We talked about polymers. We said polymers are typically long chains of carbon compounds. They are organic, which means they're carbon-based. So when you see something like organic sea salt, you can know that organic sea salt can't really be organic because it's not based on carbon. We'll talk more about that a little bit when we talk about ionic bonds later. And then we have composite materials. Composite materials can be any one of these classifications where we have two materials within one of these classifications, or they could be across classifications. I talked in my last video about how biological materials can be useful as a terminology, but it's not really an engineering classification. Things like timber, which is a biological material, it's made from a living thing, it is not a... they are themselves composites of polymers, and we mentioned that in the last video. Also, we talked about how polymers are typically made from dead trees. So again, they're also typically biological materials. There are some that are not carbon-based, but typically that's what we're looking at. So what we're going to look at here is we're going to look at the properties of materials. So there's a relatively good video on YouTube that covers the mechanical properties. I also have a link to Warwick University in the UK. I have some links here which talk about magnetism. So this is, again, Richard Feynman talking about the difficulty of describing things like magnetism, because really we're talking about stuff that is just, it's not intuitive. That we have intuitive understandings of the world, but when we start to talk about things in physics, that often what makes it useful is that it's not intuitive. If it was intuitive, we wouldn't bother learning about it. We'd just say, well, what does our gut feeling say? Whereas, unfortunately, there's no great analogy to explain how magnets work, and we really have to think about them as conceptual terms. And this is one of the reasons why people I know who've, say, studied engineering and medicine, why they typically say that they find that engineering can be more difficult, because not everyone has a good ability to intuitively understand what is going on in engineering situations, more so than the case in molecular biology, for instance. Okay, so what I'll do is I will go to the Covalent. Rather than me talking about a video that you can watch in your own time, I'm going to talk about what are the material properties. Well, we see there's a big list of material properties. So we have mechanical properties, chemical properties, physical properties, thermal properties, electrical properties, and magnetic properties. I'm just about to move the microphone. So the fact is, of all of those, we are really, as engineers, we are mostly concerned with mechanical properties. We're concerned with all of them a little bit, but we're mostly concerned with mechanical properties. And when we talk about mechanical properties, we're talking about things like strength and hardness. Now, most of you will have used these terms interchangeably. So strength and toughness, they don't really, unless you've studied them and you're using them in an engineering context. Strength, hardness, toughness, they are all kind of interchangeable. Whereas they have specific engineering terms. Ductility, malleability, brittleness, they're all these mechanical properties, and they're the ones that we're really going to focus on. That's not to say we're disinterested in chemical properties. I guess otherwise we wouldn't include them in the book. So chemical properties talk about things like how well a material, whether it corrodes, whether it rusts, whether it reacts to oxygen, whether it reacts to UV light. Those are chemical properties. We have physical properties. So this represents how dense things are. So how heavy an object is. If I have a cubic meter of it or a cubic centimeter or something, what is the weight or the mass of those things going to be relative to the mass or weight of water? we also are interested in things like porosity, and that's really useful. That's really critical if you're doing things like soil engineering. I know it's an exciting topic. I mean, every little kid dreams of one day growing up to be a soil engineer, but I came dangerously close to being a soil engineer. I was offered a job. I interviewed and turned down a job offer to be a geotechnical engineer is probably a better term, and ended up being a transport engineer instead. The next one is thermal and electrical properties, and I think that thermal, electrical, and magnetic properties, they're all pretty self-explanatory. Are they magnetic? Do they conduct electricity? Do they allow the transfer of heat very well? Okay, so let's move on. Strength is probably the one that we're often most interested in. Strength is the ability to withstand applied loads without failure. Now, I often ask kids to correct that in their textbooks, and I get them to instead say it's the ability to withstand applied stresses. Strength and stress are both measured in the same units. They're both measured in pascals. If I had been a little bit more on the ball, I might have my picture of Pascal somewhere here. Here we go. 1 Pascal is equal to 1 Newton divided by 1 square meter. So this requires a little bit of prior knowledge. It requires us to know that forces are measured in newtons, and that if we know that the force of 1 Newton over an area of 1 square meter is equal to a Pascal. Strength and stress and pressure, they're all measured in the same terms. Stress is the measure of what's being applied onto the object. Strength is its ability to withstand that load. So the idea is that it's not so much the forces that cause a rope to snap, but the area that it's being divided by. If we have the same material of chain could hold up a crane or a car of thousands of kilograms or thousands of newtons, but it depends on the thickness of the chain. If you had a chain that was only a millimeter in diameter, it's not going to be able to lift up a car. That same material, that same strength of steel, will be able to lift up a car if you have enough of it. And really, the big job of engineers, by and large, is to design structures so that they have sufficient area that they can withstand stresses, for the strength of that material. If we can't do that, we can change the material. We can use a stronger material, and sometimes we do that. Or we can rearrange our load configuration, so we can redesign the number of columns we have, or we can reinforce the structure. So there's some different options we have available to us. Okay, so the next material, and this is something that I think most kids tend to pick up through just lived experience, is hardness. So hardness, most people are aware that diamonds are the hardest material. But a diamond being a hard material doesn't mean that if you take a hammer and hit the hammer that you can't still just shatter the diamond, because diamonds are still brittle. Now, I haven't done that experiment myself. I haven't taken a diamond and shattered it with a hammer. But my understanding is that if you hit the right point of like if you hit a corner of the diamond, it will still shatter into dust. Might be a good thing to try and find a YouTube video of. Anyone watching this, please let me know. Now, hardness also doesn't mean that it can withstand a lot of load. It doesn't mean that it can withstand a lot of applied load or pressure or stress. Instead, it just means that it doesn't get scratched. It means that it doesn't get indented. So this is obviously an important property for iPhone screens. Everyone's well aware that they don't want their iPhone screens to scratch or to become indented, and that's an important property of your iPhone screen. Where this is really important is anything with a cutting blade. So obviously knives or saws or anything with a cutting blade, we really want them to have a high hardness. So swords should have a high hardness. And also anything that is in contact with moving parts. So things like gears we want to be hard, because otherwise they'll wear away. Often what we'll find as we go on with this course is that we'll have two materials in contact. And when we have two materials in contact, what we want to do is we want to ensure that the thing that is harder is the more expensive thing to replace. So if we have two things in contact, so for instance, if we have a brake pad connecting with the brake disc of your car, you want the brake disc to wear away faster, so you want it to have a lower hardness than the brake disc. Otherwise, you have to replace the brake disc, and brake discs are expensive. Brake pads are obviously and intentionally softer so that they, because they're cheaper to replace. We don't expect brake pads to last forever. We expect them to wear away, and we want them to wear away. When you put a rubber on paper, we want the rubber to be softer than the paper, because if the rubber or the eraser was not softer than the paper, well, we'd be tearing a hole in the paper, and that would be no good. Okay, so I'm really driving in home on those first two because they're the most important. I will typically give a question in the Year 11 exam that says define a material property. And if I leave it open, almost everyone says hardness is the ability to withstand scratching, abrasion, or indentation. Even if you just wrote the ability to withstand scratching, I'll give you a mark for that. I see strength less often, but I think it's a good answer. It's the ability to withstand stresses. If someone said the ability to withstand loads, I'd still give that a mark, at least in Year 11. I mean, it's in the textbook, so I can't be too harsh on you. Okay, so the next materials, these ones here, we won't really understand until we start talking about Young's modulus and stress-strain diagrams. But we're going to give it a little bit of a, we're going to give it a start, and we're going to talk about elasticity. So elasticity, as the name sort of suggests, is the ability to return to its original shape. So some objects, when we press on them or when we hit them, when we apply a load to them, they will deform, they'll change shape, but then when the load is removed, they'll return to their original shape. So a rubber band would be a classic example of this. Now, people like to talk about how rubber is not perfectly elastic, but that is definitely not the scope of this course. What I would say is an example that we like better is something like a metal ruler. So most students have had some experience with metal rulers by the time they get to this course, and they're familiar that if you take a metal ruler that you can bend, you can the metal ruler off the side of the table, and you know that when you take your finger off it, it returns back to its original position. Most people have seen a steel spring at some point in their life, and they can see, well, springs do behave elastically, and steel is a great example of an elastic material. The opposite of that, and I'm skipping one here to go to plasticity, is most people are familiar with Play-Doh or plasticine, and they're familiar that when they squeeze or squash the Play-Doh, that it will hold the shape after you've take your finger off it. It's going to stay in the shape that you've set it to. Okay, so in between those was stiffness. Stiffness is a measure of how difficult it is to elastically deform something. So if we compare those two examples we talked about before, we talked about rubber bands and steel springs, most people will be fairly comfortable with the idea that a rubber band requires a lot less load to cause it to deform than a steel spring does. If you had the same a spring sort of shape, and one was made out of steel and the other one was made out of a rubber or a plastic, most people are comfortable with the idea that steel requires a lot more load to make it behave elastically. Thank you. Okay, so the next two that we're going to talk about, they both refer to plasticity, but they refer to different kinds of plasticity. So we have malleability and ductility. So malleability is the ability to be hammered, right? So it comes from the word metallus, I think is the Latin word for hammer, to hit with a mallet. It means it can be hammered into into sheets. It says here rolled. I like the idea that if I had to define malleability, I would say it's the ability to be plastically deformed under compression, and ductility is the ability to be drawn into a wire, and that's more to be pulled, right? So we measure ductility through a tensile test, and we'll talk about material testing, I believe, at the end of this. I'll quickly talk about some of the material testing. So the last two that we're going to talk about, fatigue, is that some things can be strong enough to withstand a load, but over time they fail because of they're exposed to thousands and thousands of loadings. So aeroplanes are a good example of this, that we don't think of the wings of aeroplanes as flapping, but at a very tiny level, the changes in air pressure
do mean that those wings are constantly moving up and down, and that they're moving up and down thousands of times a day and they're flying all day every day, or virtually flying all day every day outside of pandemics, and that can cause them to fail. So this is something we need to be familiar with. We need to be prepared that a machine that's constantly working might fail in fatigue. Well below its otherwise what we'd expect for its strength. It says here its elastic limit. That's kind of a bit more of a specific thing that we'll talk about later. So lastly, we have notch toughness. So we talked about how most people would say in daily life, they'd say strength and toughness are about the same thing, whereas we do consider strength and toughness to be different things. Strength is your ability to withstand stresses, whereas toughness is your ability, the amount of energy they can take before they fail. So in this particular case, when we talk about notch toughness, I like to think of it as their ability to withstand impact. So some things might be able to, if you had a sample of, let's say, a ceramic, you might be able to load that material progressively, little by little. You might be able to load that up, and it might be able to take a lot of compressive load or compressive stress. However, if you just drop it if you drop that load onto the sample, it might fail because of the suddenness, the impact of the material. And so toughness is an important property, and generally materials that have a lot of elasticity and plasticity, they generally are fairly tough, whereas things that don't have much elasticity and plasticity, things that can't be stretched, things that don't deform very much, we call them brittle. So generally things which have low toughness typically are brittle. So when we use that word brittle, that's what we're referring to, things with low toughness, things that can't absorb much load. Now, strength and elasticity are both part of that equation, but just to give you a general term, if you had to write in an exam, if I said define toughness, the answer I might write would be the ability to withstand impact. That would be what I would write. If I had define fatigue, I would say the ability to withstand repeated loads. We've already talked about the other ones. I'm happy to move on. Okay, so we're going to blast through these other ones pretty quickly. Chemical properties, whether or not the thing corrodes, whether or not it rusts, how it reacts with other materials. So maybe some things are okay in oxygen-rich environments, but then they fail in ammonia-rich environments. Some things are okay with sulfides, other things are okay with a carbon dioxide gas, different things that they react to. On the other hand, we might talk about things like ultraviolet light being an example that causes chemical breakdown of polymers. Physical properties is we have density. So here we have the Greek letter rho. I think when we write in English, we write as RO. It's written with the Greek, yes, we just talked about here, Greek letter rho, which looks a bit like a P. The idea, I think intuitively we know that some things are heavier than others, whether or not they float on water. So in another video when I talked about how we define the kilogram, I talked about how the kilogram is defined as 1 liter of water, or at least initially that was how it was defined, 1 liter of ice water. Well, if things have a mass of more than 1 kilogram per liter, then we would consider they won't float. So oil does float on water because its mass is less than 1 kilogram per liter. On the other hand, I think alcohol is heavier. I think it goes to the bottom. That's assuming they don't dissolve. Obviously, air is lighter. Steel has a density of about 8, near enough to 8 that we can use 8. Concrete has a density of about 2.4 times that of water. So just to give you a rough idea, some humans, what's interesting is some humans are lighter than water and some humans are heavier than water, and not all water is exactly one. So people can go to the Red Sea, and I think pretty much everyone floats in the Red Sea because it's so dense, it has a density much higher than 1, and what it means is that even people who wouldn't otherwise float are able to float. Okay, so also they talk about porosity. Porosity is the number of holes that things have, and I said that earlier that geotechnical engineers care about this. Moisture content, also important for geotechnical engineers, and I'm sure for other applications. We care about how well things resist, how well they transfer heat. So I'm sure everyone is familiar with the idea of the difference between having a metal saucepan pan and a plastic saucepan pan, that when you see a metal saucepan pan, you generally want to use a pot holder to pick that up, whereas ones with the Bakelite, the plastic saucepan hands, you might be able to just pick it up without using the saucepan pan. And we also have things like thermal expansion is another property. I've mentioned in other videos, or maybe not to your year. Steel, a lot of people should have covered this in junior science, but steel, when it heats up, it expands. Most materials, when it heats up, it expands. Water is a bit of a funny one in that it also expands when it freezes. That's a bit of an unusual case. Most things heat up when they expand, and so when you have something like a bridge, that's a real concern. That the bridge, it's important that the bridge has somewhere to expand to. It's also important that when you have composite materials, that they have similar thermal expansion. So it's very convenient that steel and concrete both had expanded about the same rate. If they didn't, it would be a problem. When you're building a brick wall, you need to have gaps in the wall every 6 meters. Otherwise, expansion can be a problem. And some things like if you have telegraph poles with cables running between them, you'll notice that they sag a lot more during hot days than cold days, and that train operators or people who maintain train networks have to be mindful of that when they have overhead wiring. So that's probably a lot more than I intended to talk about that, but we'll move on. Electrical properties, how well things conduct electricity. We will talk later about how, so silver is the best at conducting electricity, then I believe copper, then I believe gold. Maybe those two are mixed up, don't quote me on that. Pretty sure silver's the best. And then we have further down the list, we have aluminium. Yet we still use aluminium because it is much lighter when you go back to density than copper. So when we're running aluminium, it's cheaper to use aluminium wires to run our electrical network, because even though it's not as good at conducting electricity, it puts a lot less load onto the telegraph poles. It's also cheaper. But when we need really good conductivity, we will use copper, and we'll learn more about the various types of copper and how very small impurities can drastically affect conductivity. Later, we'll also learn about semiconductors, and I think that's a really interesting part of the course. We're going to learn about silicon. In the previous video, I talked about the periodic table, and I talked about how silicon is right in the middle between being a metal and a non-metal, and so it behaves a little bit like it's shiny like a metal, and it does conduct electricity like a metal. But what we can do is we can allow small amounts of germanium or other boron, arsenic. We can allow those, I think phosphorus is also used, to make the silicon either slightly more conductive or slightly less conductive. And that's really important because we can use that to make switches. And these switches we put in transistors is probably the more accurate term, and diodes. Well, transistors are the basis of modern computing. Without transistors, we would not have computers. So magnetic particles. Okay, so I'm going to say, if you're interested in this, I will probably have set this for homework, that you have to read this magnetic particles. Basically, there's magnetism, and like I said, I have comments here. I do think I used to have more on magnetism. I'll maybe see if I can find more on magnetism later. Yeah. Okay. Yeah, I know that Veritasium, for instance, has a good video explaining magnetism beyond the scope of this course, though. Okay, so the next thing we're going to talk about atomic structure. Now, we don't need to know much about the atomic structure. Really, we need sort of a year 8 level, maybe year 9 level of atomic structure, but it can't hurt to just do to make sure that everyone's on the same page. Again, I'm going to be going through this fairly quickly because this video should really be for the purposes of review. So we know that everything is made of atoms, but what over time, a variety of scientists, including Thomson and Rutherford, they developed better and better understanding of how what the nature of the atom is. Obviously, we can't see atoms, so this had to be done through like the gold foil experiment and other experiments. What we eventually determined is that there is heavy parts of the atom which are all clumped together in the center, and then there's a opposite charge that is surrounding the atom. So what we're going to learn about here is that there's protons, neutrons, and electrons. For the exam, you're expected to know with those three particles. Protons have a positive charge. They only have a positive charge because we said they have a positive charge. A lot of people talk about how if we were restarting science, we might change that, we might reverse that. But for the sake of our story, protons have a positive charge. Neutrons have no charge, but they weigh almost the same amount as a proton. They weigh slightly more than a proton. We can worry about like what they're made of, but for the moment we don't need to worry that they are made themselves of smaller particles. We don't need to worry about are they bosons? I'm pretty sure they're bosons. Quarks. They're quarks. Yeah. Anyway, I don't know if quarks are bosons. I'm going to move on. The point is we don't need to worry about that. Beyond the scope of this course, right? All we need to know is that there's a positive charge, a strong positive charge in the center of the atom, and on the outside we have electrons with a negative charge or an opposite charge. Now, the idea is that generally we know that things with a opposites attract. So the electrons are attracted to protons, and two protons, they want to repel each other. Now, how they manage to hold together, which I think is a really interesting question, how these positively charged protons are all forced together when they don't want to be, when they want to be separated from each other, is by the power of the strong nuclear force, and it's this force that we tap into with nuclear weapons and fusion reactors and those sorts of things. Okay, so protons, positive charge. I think that most people find that pretty easy to remember. Protons live in the center or the nucleus of the. That's where the word nuclear, when we talk about atomic weapons, nuclear comes from, and yeah, positive charge, and they're big. They're most of the weight of the almost all of the weight of elements we can say comes from the protons and neutrons. Okay, neutrons have no charge. They're also in the nucleus. The number of neutrons can be different. So, for instance, if we have this carbon-12 and carbon-14, all carbon has 6 protons. I'm pretty confident of that. Yep, 6 protons. That's how we define it as carbon. Because it has 6 protons, that makes it carbon. Whereas neutrons, they can have any number of, well, not any number of neutrons. Typically, carbon will have either 6 or 8 neutrons. So when you have 6 plus 6 gives you a weight of 12, or if you have 6 plus 8, it gives you a weight of 14. Now, I'm pretty sure carbon-14 is the radioactive version. And what we can do, carbon dating, is we can measure, because carbon-14, all living things take in about the same amount of carbon-14, we can compare the amounts of carbon-14 that are in, say, a dead body, and we can tell if it's 100 years old or 200 years old by how much carbon-14 is left in that dead body. That's roughly how we use radiation to date things. Carbon only works for a limited amount. After that, we need to use bigger elements which have a longer radioactive decomposition. But that gives you a rough idea, and that's when we talk about an isotope. An isotope is, when we compare two isotopes, we're talking about two different versions of carbon, or two different versions of uranium, or two different versions of an element. Most elements form some amount of isotopes. And then we have electrons. Electrons are tiny. They are 1/2000th almost of the size of a proton, or the mass of a proton. And they travel around in groups, which we can call shells or orbitals. Now, generally what happens, at least as far as this course is concerned, is we're mainly concerned with, most of the time they're going to have 2 electrons in the first group, so it's hydrogen and helium. And then everything else in the next group of electrons is going to have 8. And then the next group of electrons is going to have 8. And then after that, it can be, it can vary. It could be up to 18. But for us, we're going to worry about the outside group almost always has 8 electrons. And we're going to call that the valence shell. So that's going to be relevant when we talk about different kinds of bonding. Now, previously I talked about the Eureka videos. I'm going to make this a little bit bigger. Okay, previously we talked about Eureka videos. Eureka videos also have some good videos talking about different states of matter, and I think they have one on charges. They have some chemistry ones that are quite interesting. The idea is that most people are familiar with the concepts of solids, liquids, and gases. There's also plasma, but we're not going to worry about that in this course. So
the idea, the physical things that we touch around us, we typically consider to be solid. Obviously, we're all surrounded by air, which is we are in contact with, but we don't think about touching the air as such. At least not if it's not a windy day. The idea is that these same atoms will, as they have more and more energy, they will move more and more violently. The simplest version, solids, they can be stacked in any pattern and they don't have enough energy to shake them out of their shape. Liquids, on the other hand, they have enough energy that they can't break away, but they can slide over each other. And what that means is that they can't be stacked in a shape. They will always take the shape of the container that they're in, or the base of the container they're in. And then finally, we have gases. Gases have so much energy that gases can separate from each other. They can free themselves from each other, and they can then move around in a much faster manner, and that they can fill the entirety of the container they're in. So where we say liquids take the shape of the container, it's really we'd say they take the shape of the base of the container, whereas gases will take fill the entirety of the container. What we just typically don't consider is that containers can include things like an entire room. So if we have a glass, the glass is only part of the container. It actually is part of the entire room. So a sealed container becomes more obvious. Now, there's 3 states of matter. I will probably never ask a question on that. I think that's probably assumed knowledge. Protons, neutrons, and electrons. I expect most people to have pretty good awareness of that. I will definitely ask questions on it though. Bonding. When we talk about bonding, there are 3 main forms of bonding that we're interested in. You could maybe chuck in a 4th one. We could talk about secondary bonding, also known as van der Waals bonding. Are you familiar with that? Van der Waals, London forces. Never heard of that? Okay, so it might be worth mentioning that quickly. Okay, so the first one here is we have ionic bonds. If we're talking about now, I don't go into a lot of detail here, so let's just. I'm not going to read through this document. What I'm going to say is that, and I've already. If I go back to the Facebook, I can show you my notes on that. Okay. So in this here, I talk about how everything's made of atoms, and I talk about valence electrons. And when I talk about valence electrons, how I talk about sometimes we have good pairings. So I don't know why I don't get periodic tables up before I start. Okay, it's a YouTube video. Go back. Okay, so if we're looking at the periodic table here, that these ones here, they have 1 electron in their outer shell. They have 2. So if we take lithium has 2 in its first shell, which that makes sense. We always said that the first shell always has 2 electrons, and it has 1 left over. If we look at sodium, it has 2 in its first shell, 8 in the middle shell, and then another 1 left over. Magnesium has 2, 8, 2. If we take, say, calcium, it has 2, 8, 8, 2. Now, everything in this row, it has 1 valence electron on the outside. So we could kind of think about if I'm at my board game group, and there are 20 people there. So if I look at number 20, calcium, well, the first 2 people, they're just happy playing a 2-player game, and the next group of people, they're happy playing an 8-player game, and the next group of people are playing an 8-player game, and then I have calcium left over, so that means that there's 2 people who are not playing a game at the moment. And what they'd really like is they'd like to join, in the case of calcium would really like to find somewhere for those 2 leftover players for them to go. So what they really want to do is they want to find a situation where someone who's only got 6 players, they really want to meet up with someone who's got 2 left over. Now, this row here, everyone here has exactly the right number of players. Helium has 2 ready for a 2-player game. Neon has 2 playing the 2-player game and another table of 8. Argon has 2, 8, 8. So if we look at oxygen though, oxygen has 2 players left over. It has 2 and then 6. And it really wants to have 8 in that outside shell. So calcium and oxygen, they go together really well. They pair up, and suddenly the 2 left over from calcium, they're happy to go and play with oxygen, and everyone's happy. Another example that works out really well is sodium and chloride. Sodium has 1 too many, and chloride has 1 too few. So when we do that, when we get that combination of a metal and a non-metal, when they join up like that, we typically call that ionic. That's typically going to be ionic bonding. Now, when we have ionic bonding, they're going to form a lattice. So I'm going to write ionic a lattice or a crystal. And in this crystal, everything is just perfectly balanced in position. The positively charged and the negatively charged are all held just in the right spot. Now, when I say positively charged and negatively charged, the chloride ion, he's lost an electron. So he's now, the chloride ion has gained an electron, so he's now negative. The sodium ion has lost an electron, and because electrons, they're a bit of a downer. When you lose the electron, you're like, hey, I'm happy. Everything suddenly, my life is a lot less stressful. On the other hand, chloride has sort of taken on, that toxic friend, and now their lives are a bit more stressful, and so they're a bit negative. And so the idea is that whenever they lose that electron, we call that an ion. I kind of skipped that step. That is covered in my notes when we do this in class. But the idea of losing or gaining an electron turns you into an ion. And if you've gained an electron, well, you're now a little bit negative. So you're a negatively charged ion. And if you've lost an electron, you're now a positively charged ion. And what we can see here is that these ions, these positive and negatively charged ions, they're held together in this perfect balance, in this perfect crystal of crystal lattice. Now, what we'll find out is metals also form an ionic lattice, but they're all positively charged. There's no negatively charged one. So that's when we talk about ionic bonds. Now, when we have something like salt, if we dissolve salt, if we take some tablespoons of salt and we put them in water, we'll find that the solid will dissolve. And what will happen is that all of these ions, they will be broken up because water has such a strong electromagnetic charge. The water will come in and it will separate these positive and negative ions. And when you separate those bonds, they all fall apart. The same thing happens if you take a hammer to an ionic bond. If you have a crystal made out of an ionic bond and you hit it with a hammer, it's entirely possible that force will be enough to shatter the crystal, and it won't reassemble easily because it's just held together in such a delicate balance. So that's the case for ionic bonds. We're going to get to metallic bonds later, so I'm going to leave that one ready to go. Okay, so that's what we're looking at here. We have lithium. Lithium has 1 too many electrons. It goes to fluorine. Now fluorine's, well, you'd think fluorine's it's actually negatively charged, and the lithium ion is positively charged. We put them together in a lattice. Okay, covalent bonds are a little bit more complicated, but this diagram does a relatively good job, and this is the one that we encounter a lot of, particularly things that are living things. We cover this a lot in chemistry. So in a covalent bond, rather than something giving up or taking away, gaining or losing an electron, what happens is they form a partnership where they just agree to share the electrons. So hydrogen, we look at hydrogen on the periodic table. It sits up in on its own. It has 1 electron and it needs 2. Well, what happens if they both meet up, they both share, and they both feel as though they have 2 electrons in this configuration? Now, when I talked about water having a polar bonding, what that sort of means is that this side of the hydrogen atom is going to be slightly positively charged, and this sort of side of the molecule is going to be slightly negative charged because there's the 2 electrons there. And when that goes through a ionic bond, it can be, especially for water, water has very strong polar bonding. It can be enough to disrupt other things. And that's why water makes a good solvent. It dissolves things well. And when we talk about water being a good solvent, that means it cleans things. It separates the dirt from your skin. It separates the dirt from the dishes. Obviously, there are much better solvents, like alcohol is a better solvent, or dishwashing liquid is a better solvent. And it just separates the bonds between things. Polymers are an engineering application of covalent bonds. It's worth pointing out above ionic bonds that ceramics are often made of ionic bonds. Okay, so covalent bonds, if I had to define this, I would say an ionic bond is a lattice of positively and negatively charged ions. If I had a question said, define an ionic bond, that would be what I'd write. An ionic bond is a lattice or a crystal of negatively and positively charged ions. Covalent bonds are where two or more elements share electrons. That would be my definition. That's probably good enough for us. And then we have metallic bonding. Now, metallic bonding, I often use the example of dads at the barbecue. We have only positive ions here, right? Only good vibes. These dads, they've gone along, they've taken their one electron kid, and they've gone to the barbecue and they've said, okay, kids, run around and have a good time. And no one dad can see his kid, but they know there's enough dads out there that the kids are being looked after. If anyone gets up to real mischief, one of the other dads will say something. And those kids, they just run around crazy. And that's how we can have electrical charges move through here. Because the electrons are free to run around and do what they want, they can be very easily used to carry electrical charge. If someone asked me to define a metallic bond, well, I would probably draw a picture, because drawing a picture can help to explain things. And I would write that a metallic bond is made up of a lattice or crystal of positive ions surrounded by an electron cloud, or a dislocated sea of electrons. Yep, that's another way of writing the same thing. A metallic bond is made of a lattice of positively charged ions surrounded by a dislocated sea of electrons, or just an electron cloud. Okay, we've moved on that. Okay, so we're calling them, I think that we stopped calling them van der Waals forces because it sounded too German, and during World War I or II, they instead decided they were going to call them London forces or secondary forces. The idea is that when we have, say, hydrogen atoms or H2O atoms, what holds the H2O atoms together? Well, they're held together by these intermolecular forces, the van der Waals forces. That's what holds them together. That's what keeps those oxygen particles from bouncing. When they bounce around, what keeps the oxygen more or less together is these secondary forces. In the case of water, we talked about they have stronger forces. We actually call polar forces, but that's not something that I learnt when I was in high school. I think you might have to do it in chemistry. I definitely learned it when I did engineering, but I don't think it's really something that's likely to be tested in the new HSC course. If they said, what are the forces? I would think it'd be pretty mean to have a question that says, what are the forces that join covalent bonds? But if you wrote secondary forces, I would give that correct. Okay, polymorphism. Okay, so well, first of all, to know what polymorphism is, let's just break that word down. Poly means many, morphism means shape, right? That it can hold many shapes or many structures, something along those lines. Now, the idea is that we talked before about how salt forms a crystal, right? So when we talk about table salt, it forms a crystal. Rust forms a crystal, a lattice of ions. And we talked about how metals form a crystal. The ions are surrounded by a sea or an electron cloud. Those crystals can arrange in different ways. So when we talk about those crystals arranging in different ways, well, we need to know about crystal structures. Now, some things can form in multiple crystals. Steel can form multiple crystals. Carbon can form multiple crystals. So graphite, graphene, diamond, they're different formations of carbon. So different materials have different crystal structures. And when that happens, we can call them polymorphous. Some things don't form a crystal structure at all. We call that amorphous, which we just learned about here. I will talk about both of those. Now, we should have covered this. When we did crystal structures, but we can close that, and we're now onto our next one. These are the crystal structures we are most interested in. When we're talking about non-crystal materials, I had a big fight with my father-in-law once about glass being a liquid, and I have a video too, I think a Veritasium video, but it could be something else, explaining that glass is in fact not a liquid. Not something I want to debate in this class, but glass not a liquid. It's just a non-crystalline solid. It just means it doesn't follow, the atoms in glass don't follow a rigid crystal structure. They're all they're higgledy-piggledy. Whereas most structures we look at, they follow a much more regular crystal structure. They're polymers or plastics. They can be crystalline or semi-crystalline. So that's what we have here. Amorphous, so acrylic, polystyrene, polycarbonate, ABS, and PVC, they're all non-crystalline. Whereas some are semi-crystalline, so most of the others, when we have like polyethylene, polypropylene, PET, so most of the ones here we have number 1, number 2, number 3, number 4, number 5, number 6, so all of the numbered ones, which we're going to learn about later, they're all here. Okay, so when I think about crystals, a good way of looking at this is the way that we could stack fruit.